So we're ready to learn how to find inverse functions. So I've outlined some steps here for you. The first step says to first determine if the function is one-to-one. We'll just stick with using the horizontal line test to check that. There are some algebraic methods we could use, but it's a little bit of a challenge. So if we have a function that is one that we don't really know what the graph looks like, I'm just going to tell you that it's one-to-one. So pay attention to the directions, and if it says it's one-to-one, you can skip that part, okay? Save yourself some effort. And then in step 2, once you know it's one-to-one, we're going to interchange x and y everywhere in the equation y equals f at x. So like in this one here, we'll replace this with y and then switch the x and y. And then we'll solve for y. And what that process, 2 and 3 together, what that does is basically give us the opposite operations that we need in the right order. So that kind of just keeps track of everything for us, so we don't have to just figure it out in our head. Step 4, once we get y isolated, that should be our inverse function, but we want to be careful and make sure that that result is also a one-to-one function. If it's not a one-to-one function, we're going to restrict the domain to make it one-to-one. If it's not one-to-one, it's not the true inverse. But we can make the adjustment needed to get the true inverse. And then I always want you to use the inverse notation for your final answer. So replace y with the correct notation so it's clear that they're inverses of each other. Alright, so let's do some examples. We have some functions here. We want to find the inverse if it exists. So the first one is a linear function. And if you think about a line, as long as it's not a horizontal line, and of course can't be vertical because then it wouldn't be a function. So it's a function and it's not a horizontal line, then it's got to be invertible. It's going to automatically pass the horizontal line test. So let's just put in parentheses here, linear functions with a slope not equal to 0 are always invertible. You can of course graph this, but I think we don't need to do that, and you can understand that's only a horizontal line is only going to cross this one time everywhere on the graph. Okay, so the inverse exists. We're going to write y equals f at x. And then we're going to interchange x and y. So I always use this to kind of show that's what I'm doing so it doesn't get confusing from one step to the next, like what the world just happened. Everything looks different, right? So I put this here to show that is what's going on. And then we're going to isolate y. You hear I'm sure you can hear my dog, I'm sorry. So her mortal enemy is the UPS truck, and I think that's who's driving by. Either that or it's the mailman. But she really hates the UPS truck. She's weird. Okay, so we're going to isolate y. So we could do this 2 ways. Add 2/3 to both sides, and then multiply both sides by 2 to get rid of the 1/2. And now we've got 2x plus, distribute, right, 4/3 equals y. Or if you wanted to, you could also clear the denominators first. Like when I said 2 ways, that's what I meant. You could multiply both sides by 6 and get 6x is 3y, right? 1/2 times 6 is 3, minus 3 goes into there 2 times 2 times 2 is 4. And then 6x plus 4 is 3y, and then divide both sides by 3. And then you could leave it as 6x plus 4 over 3, or if you split it into 2 fractions, you end up back here. Whatever way you write the answer is fine, or whichever way. Now, notice that this result is also a line, and therefore it's going to be one-to-one. So, because linear functions are always invertible, they're always one-to-one. I could write slash one-to-one, right? Those things go together like we discussed. So our final answer, f inverse at x, is I'll use the slope-intercept form, 2x plus 4/3. So linear functions, they're always going to be our easiest problems to do. You know, it's very easy to solve for y in a linear function, you know, after you interchange x and y, and the inverses always exist. There's nothing really to check on those. All right, in B, we have the squaring function or the quadratic function 2x squared minus 3. And we know from the work we did with graphs that this would be a parabola shifted down 3 units, and the 2 makes it skinnier. But you know, your graph doesn't have to be real accurate. As long as you understand that it's a parabola, you immediately can see that a horizontal line, assume mine's horizontal, which it's clearly not, but a horizontal line would fail, right? Crossed more than once, so fails HLT, so G inverse does not exist. And that's all we have to do for that problem. You shouldn't put y in there and interchange the coordinates and try to solve. That would be a waste of time. It's important you check this first. Save yourself that effort. All right, okay, so C. So here we've got the cubic function shifted 3 units to the right. This stretches it and this moves it up, but the stretch and the moving it up isn't, you know, and the shifting doesn't really matter. You understand the basic shape is that S shape, kind of, you know, curve, kind of. I'll graph it a little bit more accurately than that. It moves over 3 and up 2, and the 2 stretches it. But it's clear to see, even with a rough sketch, that this would pass the horizontal line test. So H is 1 to 1. This looks like one word. It's supposed to be so, or therefore, H is 1 to 1. So we will go ahead and replace H at x with y. And then we'll interchange x and y. So x is 2 times y minus 3 cubed plus 2. And then we're going to solve for y. So we don't want to cube this. If you do that, you're wasting your time. That will make it harder to solve. We're going to reverse the operations here. First, subtract 2 from both sides. So x minus 2 is 2 times y minus 3 cubed. Then we'll divide both sides by 2. X minus 2 divided by 2 equals y minus 3 cubed. And then take the cube root of both sides. Cube root of x minus 2 over 2 is equal to y minus 3. Right, so that this is cubing, so the inverse would be cube root of both sides. And now add 3 to both sides. So y equals the cube root of x minus 2 over 2 plus 3. Now we want to make sure that this result is also 1 to 1. So is this 1 to 1? And if you understand what the cube root function looks like, then you know that it is. Remember, the basic y equals x cubed looks like this. Or I said x cubed, I meant to say cube root of x. This, you know, shifts it up. This shifts it to here. Let me come down here, show you something. So this gets a little like hard to interpret, I think, the way it's written. You might be a little confused. But what you can do is rewrite this as 1/2 times x minus 2 under the radical, and then cube root of 1/2 times cube root of x minus 2 plus 3. And then think of this as a vertical stretch or compression. This shifts it 2 to the right, and this shifts it up 3. And so if you know the basic shape, you understand none of these things are going to sorry, I lost track of what I was going to say, are going to change the fact that this is 1 to 1, right? And so this is 1 to 1. I'll just make a note there. So the inverse function, h inverse at x, is, and you can write it like this, or you can write it like this, it's up to you. I'll just write it like this, it looks a little neater. Cube root of x minus 2 over 2 plus 3. Okay. All right, and then in D, I give you this function. This, again, this is that similar to that G composed with F, F composed with G example. It's the same type of function that we haven't dealt with yet. So that's why I made a note that R is 1 to 1, so you can skip checking that. Now sorry, so let's just go ahead and replace R at x with y. I got 2x plus 1 over x minus 3, and then we're going to interchange x and y. So we've got x is 2y plus 1 over y minus 3. And this is a little tricky to solve for y because you've got y in the numerator and the denominator. What you want to do here is get rid of the fraction first. So multiply both sides by y minus 3. You can also kind of think of it as cross multiplying if you like that. And then distribute xy minus 3x is 2y plus 1. Okay, so what happens is you've got two terms with y in it. You want to group those on one side and move everything that doesn't have y to the other side. So this implies, let's move the 2y over here, xy minus 2y equals, and then add 3x to both sides, 3x plus 1. And now how can we get y alone? And the trick is, notice y is in both of these, so we can factor it out. That's why we want to group all y terms together. Then we can factor out the y. And then y is 3x plus 1 over x minus 2. Now again, we end up with the same type of function. It's called a rational function. And again, it's hard to tell if this is 1 to 1 if you don't know more about those functions. So on these ones where I tell you it's 1 to 1, just assume the inverse is also 1 to 1. You don't need to worry about checking those ones. Okay? And whoops, this is R. I want to make sure I use R. So then R inverse at x is 3x plus 1 over x minus 2. One thing I could show you here is how the domain and range do end up, as we discussed. In other words, whoops, that's not what I wanted to look at. Where is that page? Here. The domain of f equals the range of f inverse, range of f equals domain of f inverse. This kind of is related to number 4, checking if it's 1 to 1. So let's go back to where I've gotten so with my pages here. So like with the linear function, this is easy. The domain and range of this is all reals. And the domain, you ended up with a linear function for an inverse, and so the domain and range is all reals, so that's automatically satisfied. For the same with the cubic function and the cube root function, those are, domain and range are both all reals. But here, notice for R, the domain of R is everything except for 3. So negative infinity to 3 union 3 to infinity. Now the range is not clear just by looking at this, but what we can do, if we look at the domain here of R inverse, notice that's negative infinity to 2 union 2 to infinity. So what we know about from our discussion about the domain of this should be the range of this, and the domain of this should be the range of this, that this 2 here is also excluded from the range of R. It should be the exact same set. And what that means is no matter what you put in place of x here, you're never going to get the result 2 for your output. And so if you try to solve 2 equals 2x plus 1 over x minus 3 to see if there is an x that would give you this y, what will happen, notice when you solve, multiply both sides by 2x minus 3, you've got 2x minus 6 equals 2x plus 1. Notice negative 6 does not equal 1. That's false. So this equation has no solution. And that's showing that 2 is in fact not in this range. So the range of r, I don't know why I used a capital R here because it's little r for the function, and that does matter, capitals versus lowercase. And likewise, we could show a similar statement here that this will never equal 3. You're never going to get an answer or a value of x that will give you an answer or a result of 3. So the range of r inverse will equal the domain of r. Now when we discuss these rational functions, it's going to be clearer how the domain and range, okay? The domain, we have already actually done problems like this. I should say the range. It'll be, you know, we're going to discuss how to find the range. I just wanted to show you that, you know, those numbers that are excluded are also excluded from the range or domain. Hopefully that makes sense. I'm kind of trailing off there. All right, so let's do the last problem. Here we have the square root function, this time cap r at x, 1/2 times the square root of x minus 3. And we want to find the inverse function. Now r is 1-to-1, if you remember what the function, well actually I'll just use this here because we're going to sketch the graph of r and r inverse on the same plane. So we might as well go ahead and start with sketching r. So this will be our square root function shifted 3 to the right, and then the 1/2 is going to vertically shrink it or compress it towards the x-axis. So when we plug in like 4, you know, we get square root of 1, but then half of that. So it's a compression. And when we go 1, 2, 3, 4, that's 7. 7 minus 3 is 4. Square root of 4 is 2. 2 times a half will just give us a height of 1 instead of 2 like in the original. Okay, so here's 1, 2, 3, 4, 5, 6, 7, 8, 9. Normally that would go up to 3, so this is going to be at 1.5. Okay, so here is our okay. Clearly that's 1-to-1. You always want to check that. It would pass the horizontal line test. Alright, so let's go ahead and take y is 1/2 times the square root of x minus 3. Interchange x and y. We get x is 1/2 times the square root of y minus 3. So first let's get rid of this half. We multiply both sides times 2. We've got 2x equals the square root of y minus 3. And now we're going to square both sides. And we get 4x squared equals y minus 3. And then when you add 3 to both sides, 4x squared plus 3 equals y. Okay, so here's an example where we have a problem with that the function that we get ends up not being 1-to-1. That's a quadratic, and we talked about how the parabola is not 1-to-1. Okay, so we have a problem. This is not the true inverse of this. And the problem arose when we squared both sides. What will happen when you square both sides of an equation is that the result has more numbers that make it true than the original. So notice on this, in this step here, because this is equal to a square root, the x's here can only be positive. But at this step, the x's can be both positive and negative, and you know, like if x is -1, for example, you've got 4 is y minus 3, and so then y, you know, that would have a solution. But up here, when x is -1, there's no solution. And so we get more values that work in place of x for the result than we do with the original equation. Well, let's look at the graph. 4x squared plus 3, that would be squaring x squared graph, shifted up 3, and the 4 makes it skinnier. So if you go out 1, instead of going up 1, you're going to go up 1, 2, 3, 4. 1, 2, 3, 4. And if you went out 2, you would go up 8. That's going to be quite a ways up there, so I won't graph it, but you can visualize where that would go. Okay, so you have something that looks like this. And of course that fails the horizontal line test. So what we want to do is restrict this domain so it's 1 to 1. And basically we can do that in two ways. We can either take this half of the parabola or this half of the parabola. And we want to pick the half that has the ordered pairs of this just switched around. And it's going to be the ones with the positive x's, because notice these all have positive x's. That's the domain of this matching up with the range of this, okay? And vice versa. You need both of those to work. Notice this one has the domain of 3 to infinity, and the range is 0 to infinity. This one, the range, okay, so the domain of this one, just look at the graph, is all real numbers. And the range is what we want, which is 3 to infinity. Right? We want this to match up with this, and they do. But notice these don't match. And that's because it's not 1 to 1. If it were 1 to 1, we want it to match. So we need to pick this range. We want these x's to only be positive. And again, that comes into play with what we talked about up here, where these x's can only be positive because the square root is positive. There's lots going on, and you know, to think about here, but the shortcut is just, okay, whatever this range is, that's what you're going to pick for your domain of your inverse function, so that you restrict it and it becomes 1 to 1. So we want to cross out this part. Just this part is our inverse. Okay. The green graph is R inverse at x. I'll just write R inverse. So R inverse at x is going to be this formula, but only on 0 to infinity. You need this. If you don't have that, it's not the true inverse. This is 1 to 1, right? That would pass the horizontal line test. And notice that then, you know, this is not the domain of R inverse. Now its domain is what we want, 0 to infinity, because we've restricted it and made it what we need. Okay? Now the last thing I want you to realize about a function and its inverse is that their graphs, because you're switching all of the ordered pairs, notice this is 3, 0, this is 0, 3. This had 4, 1/2, and this one has 1/2, 4. This had 7, 1. This one has 1, 7 right there. Because of that inversion of the coordinates, these graphs will always have the relationship that they are reflections through the line y equals x. So, right, y equals x is the line with a slope of 1 and an intercept of 0. That relationship always holds. So like on a test, I might just give you a graph of a 1-to-1 function and ask you to graph its inverse. You would do that by reflecting it. And that can be a little bit hard because you're reflecting through a line that's at an angle, but use your ordered pairs to help you. If you see any ordered pairs, just invert them and kind of get an outline of where the graph goes. Okay, so remember that's a reflection through y equals x, and that is, I said we would put number 6 in here. That's the last one. The graphs of f and f inverse are reflections of each other through the line. I know I'm writing fast, but because this is video, you can always pause, right? Y equals x. Okay? So lots to think about, lots of relationships between functions and their inverses. If you have any questions about that, please let me know.